Hi student, welcome back. So we have learned about Darcy's equation, which is Q equals to negative K times area time difference in height divided by the length. So let's see how much valid is Darcy equation. So because Darcy did his experiment through a tube filled with sand, so I use my marker as a tube in this lecture, and the water is flowing from the higher pressure to the lowest point of, and then he put 2 manometers to well, as you remember from the previous video. So let's see how does this experiment valid. First of all, in this experiment we have ignored kinetic energy. How about the movement of the particles, which is also involve low velocity? We also assume that a laminar flow is happening throughout the pipe, throughout the groundwater flow. But laminar flow is actually just when the water there is no resistance throughout the water. But actually water sometimes flow through turbulence. So this is where we need to remember to take into account about Reynolds number. So actually Reynolds number is, we have to calculate the Reynolds number. Reynolds number is actually the initial forces divided by the viscous forces. So viscous forces is about viscosity forces. What is actually viscosity? Viscosity is actually how resistant the fluids to flow. We can have dynamic viscosity or kinematic viscosity. In our groundwater, we usually use dynamic viscosity, as dynamic viscosity is showing something that has been pushed sideways with shear stress. So apart from that, we also have to specify specific discharge area and the effective grain size diameter. So this is if we want to go in details of the groundwater flow. With this, we can say that Darcy's law is only valid for Reynolds number smaller, less than 1, or maybe we can use up to 10. So the range is with Reynolds numbers 1 to 10. So this is the graph showing specific discharge Q, means this is really how much discharge has been going through from the input to output, and the hydraulic gradient. So if we plot this using turbulent flow or the Reynolds number using RE more than 100, we can find that Darcy's equation is only applicable in the range of 1 to 10 of Reynolds number. So the hydraulic gradient, we plot this hydraulic gradient, and this is the range of applicability for Darcy's law. So if we have a very turbulent flow, our sediments is not flowing nicely, means we have during rain season or flood season, then this equation is not applicable anymore. So in general, Darcy allows an estimation of the velocity of flow rate moving within the aquifer, the average time of traveling from the head of the aquifer, top of the aquifer, to the point located downstream. So this is based on higher point to the lowest point. So if we have 2 wells, from the highest well to the lowest well. It is also very important for prediction of contaminant plumb arrival. So contaminant plumb arrival is referring to if we have a contamination in our groundwater, we can check, we can estimate, we can hypothesize how long does this contamination will be arriving in our groundwater, and then will then be flow into the human source or the source of when we extract the water for our daily purpose. So in conclusion, As you can see here, this is one of the famous experiment to imitate how Darcy did his experiment. So you can actually Google or check in YouTube how does these people conducted this experiment. So they put wells in the higher slope and they put different sediments size, different gravels, different grain size. So they see how much the flow rate for in each of these sediment sample. So in conclusion, if there is no pressure gradient over a distance, there will be no flow. So this is of course the case of hydrostatic, means your water will not be flowing if it's at the same level. Thus, if we put a pressure gradient, we gonna allow water to flow from high pressure, from the highest point to the lowest point. Thus, this is showing the opposite direction of increasing gradient. We are flowing from highest to the lowest. We are supposedly to increase our gradient, right? But because we are flowing from highest to lowest, this is the reason why we have to put the negative value in our Darcy's equation. So the greater the pressure gradient, as though we going through the same formation of material, it will be the greater discharge area. So means if it's higher point of the pressure, two different level of pressure throughout the same material, the rate of discharge for Darcy's equation will be higher. So if the discharge rate of fluid will often be different through different materials, or even same material at different direction, even if same pressure gradient exists. So you have to remember this thing, that in Darcy's equation or groundwater flow, we have to take into account first hydraulic conductivity, which is K, velocity. We have two types of velocity. Velocity Darcy, VD, which include the whole area, of seepage velocity, which is only the void's velocity. We also have to take note about viscosity, which is the resistance of fluids to flow. We also have to take note about pressure difference in the well head. We also have to take note about Reynolds number, means is it laminar flow or turbulent flow. And apart from that, we also have to take note about gravity, because gravity is everywhere on Earth and the water is actually flowing through gravity. Then to go in details, we can talk longer about this, but these are the parameters I mentioned earlier that you have to take note about how groundwater flows, and you need to know about Darcy's equation as a basic for groundwater flow. Okay, that's all for this lecture, for Darcy's equation lecture. So tomorrow at 2 to 4 p.m. we are going to have in-class exercise for Darcy's equation, and please bring your calculator because we are going to do a little bit of numbers and calculation and put in the Darcy's equation. So I hope this is going to help you to do a preparation study before you entering the class. And in the class, we're going to have this exercise apart from continuation of the groundwater lecture from last week. So that's all. See you guys tomorrow.